Before there was light, there were shadows. The newborn universe was not a blaze of creation, but an endless hush. No stars, no galaxies, no warmth, only an invisible sea expanding into nowhere. Space itself was young, its energy still trembling from the birth it could not remember. There was no color, no shape, no sound, only the faint pulse of gravity whispering through the dark. This was the age before dawn, a time when hydrogen and helium drifted like ghosts, waiting for the first spark. Yet even in that silence something stirred, something ancient, hungry, and unseen. Black holes, born from collapse, not creation. They may have formed before the first stars had a chance to shine, swallowing matter before matter could even dream of becoming light. It defies the story we tell ourselves. That light came first, carving meaning from the void. But what if the universe began in reverse? What if the first architects were not suns but abysses? Imagine a cosmos where gravity, not fire, was the first sculptor, where darkness wove the threads that light would later follow. In that primordial stillness, invisible wells curved the newborn fabric of space-time, pulling matter into silent spirals. Long before the first sunrise of the cosmos, these unseen giants might have been shaping the very scaffolding of galaxies yet unborn. The great paradox unfolds. Perhaps the universe didn't begin with illumination, but with collapse. Before the light could reveal the cosmos, the shadows had already begun to build it. Light hadn't yet been born, but something was already dying. The universe began not as a scene of radiance, but as an aftermath, a soft cooling from unimaginable heat. In its first second, the cosmos was dense beyond comprehension. A storm of particles and energy condensed into a single expanding breath. Matter and antimatter annihilated in pairs, leaving behind a ghostly surplus, the faint residue that would one day become everything. Then, for the first time, the universe began to slow. Its temperature dropped, its fury softened, and from that decaying storm emerged the possibility of form. Roughly 380,000 years after the Big Bang, the light finally met resistance. The universe cooled enough for electrons to bind with protons, forming neutral hydrogen. It was called recombination, though in truth it was the first true combination, the first stable atoms. Before this, light could not travel freely. Photons were trapped, bouncing endlessly between charged particles, scattering in a brilliant fog. But as atoms formed, that fog cleared. The first light, the cosmic microwave background, burst forth, stretching across the entire universe. Yet this was not the light of stars. It was not the glow of galaxies. It was a fading whisper, red-shifting into invisibility as space itself expanded. The universe entered its longest night, a time known as the cosmic dark ages. Hundreds of millions of years where nothing burned, nothing glowed, and no new light was born. To an observer adrift in that darkness, the cosmos would have seemed endless and empty, a silent ocean of hydrogen gas. But beneath that stillness, gravity was at work. Tiny imperfections, quantum ripples frozen into the expanding fabric of space-time during inflation, had left subtle fingerprints on the density of matter. Some regions were infinitesimally denser than others, and gravity, patient and unrelenting, began to pull on those differences. These were the seeds of all structure, the faint bruises in the newborn universe, that would someday become galaxies, clusters, and filaments. They were the universe's first imbalances, and from imbalance came destiny. In most places, gravity's pull was too weak to overcome expansion. Matter drifted apart, too diffuse to clump together. But in rare places, where those primordial fluctuations had stacked, amplifying one another, density soared. Gas and dark matter began to gather, forming invisible halos long before any starlight appeared. And within those halos, something strange might have happened. According to some models, if a region became dense enough, and if cooling was slow enough, it could have collapsed directly into a black hole, skipping the birth of a star entirely. These were primordial black holes, cosmic phantoms born from gravity alone, unlit and untraceable, forming in the earliest epochs of time. In the first second after the Big Bang, such conditions may have existed everywhere. Density fluctuations weren't just subtle. In some pockets, they were extreme. The tiniest overdensities could have collapsed under their own weight, forming miniature black holes the mass of mountains or moons, or even billions of times heavier. Some would have evaporated almost instantly, vanishing in bursts of Hawking radiation, their deaths flickering across a sky that had no eyes to see them. Others may have survived, wandering the cosmos still, hidden within galaxies, invisible but gravitationally potent. Fossils from before the first light. Imagine that. Black holes older than the stars themselves. Death before life. Collapse before creation. The paradox deepens, for if black holes were truly the first structures, then the story of the universe began with gravity devouring its own child. Before the first stars could shine, the cosmos was already haunted by their end. But to understand how that could happen, we must return even earlier, to the very first moments when quantum fluctuations rippled through a universe smaller than an atom. Inflation, a brief, furious expansion, stretched those fluctuations to cosmic scales. What began as subatomic tremors became the scaffolding of the universe. The fabric of space-time itself carried these imprints, regions slightly denser, slightly colder, slightly heavier. When the inflationary storm ended, those ripples froze, scars in the geometry of everything to come. Over millions of years, they would dictate where galaxies would form, where voids would stretch, and perhaps where the first shadows would collapse. In those dense spots, where pressure and gravity wrestled in silence, hydrogen gas began to swirl. It was a slow process, far slower than any explosion, a cosmic patience that spanned eons. Gravity is not impulsive. It waits, it gathers, it tightens its hold with invisible persistence. And so, in the void, these ripples deepened into wells. The fog of hydrogen drifted into them like mist sliding down a valley. In some, the collapse led to turbulence, heating the gas until it could ignite and form the first stars. But in others, the collapse was too rapid, too immense. The atoms never had a chance to fuse. Instead, space itself folded inward. A black hole was born, not from the death of a star, but from the hunger of gravity itself. Light hadn't yet been born, but something was already dying. Scientists call this possibility direct collapse. The idea that supermassive black holes, weighing millions of suns, could form almost instantly in the early universe. These titanic shadows might explain a cosmic mystery, how quasars, the blazing hearts of early galaxies, appeared so soon after the Big Bang, too massive to have grown from normal stars in such little time. If true, then black holes didn't just arrive early. They preceded the dawn. They may have shaped the flow of matter, drawing gas into vast filaments, accelerating the birth of galaxies themselves. In this sense, darkness wasn't the enemy of light. It was its architect. Still, this ancient epoch defies human intuition. For us, darkness is the absence of information, a void. But in the early cosmos, darkness was information. Every unseen wave, every silent density fluctuation carried the blueprint of everything that would follow. The cosmic dark ages were not empty. They were gestational, a vast cosmic womb filled with potential energy, with invisible tides already carving the universe's first landscapes. Imagine drifting through that time. No stars, no planets, no warmth, only the faint afterglow of the Big Bang stretching to red oblivion. You would see nothing. You would hear nothing. Yet, around you, entire galaxies were being whispered into existence by gravity alone. Everywhere, dark matter was gathering, its invisible halos merging and growing. These halos were the skeletons upon which luminous matter would later cling. They created the cosmic web, the great interconnected lattice of filaments that still defines the universe today. And within the densest knots of that web, the first black holes may have stirred. They were silent, consuming nothing yet, merely existing as potential wells, invisible hearts of gravity awaiting their first meal. As time passed, baryonic matter, normal atoms, began to drift toward these halos, cooling, collapsing, spiraling inward. It was the universe's slow inhale before the first blaze. But not every region was destined for light. Some would never ignite. Some would simply fall, collapsing into darkness so complete that even the concept of illumination would not apply. The irony is beautiful and terrible. Before stars learned to shine, the universe had already discovered how to fall. Around 100 million years after the Big Bang, this gravitational choreography continued in silence. The first proto-galaxies began to take form, faint and shapeless, drawn together by the unseen influence of dark matter. And in their centers, black holes, whether born from direct collapse or from the primordial seeds of inflation, began to grow. The fog of neutral hydrogen still cloaked everything, blocking light from escaping freely. Astronomers call this the dark curtain, a cosmic veil that would not lift until the first stars and galaxies ionized the universe. But behind that curtain, the stage was already set. The first shadows had taken root. Today, we search for traces of that invisible era. We map the faint ripples in the cosmic microwave background, looking for the fingerprints of those early overdensities. We model how matter might have collapsed before starlight, testing the idea that black holes could have come first. And though we cannot see them directly, their influence might still echo. In the mass of galaxies, in the structure of clusters, in the very distribution of matter itself. If primordial black holes exist, some might be drifting through the Milky Way even now, as small as asteroids, as heavy as mountains, perfectly dark. We would never know unless one passed through a star's light, bending it ever so slightly, a gravitational whisper across billions of years. It is humbling to think that the oldest things in existence might be invisible, that the universe's first creations were not made of light, but of collapse. When the first stars finally ignited, hundreds of millions of years later, their brilliance did not banish the dark. It only revealed how much of it there was. For every luminous galaxy we can see today, there are countless voids, each shaped by gravitational scars that stretch back to those earliest fluctuations. The darkness was never gone. It was merely waiting. The first black holes, if they truly existed before light, would have been the sculptors of destiny. Their presence determined where galaxies would form, how fast stars would gather, and how the cosmic web would thread itself across eternity. In this sense, they were not intruders in creation. They were its foundation. The universe, in all its luminous splendor, may have been born from the womb of darkness. Every photon that now races across the cosmos, every atom that burns in a star, may trace its lineage to those first invisible collapses, to the shadows that predated light. So perhaps the truest story of creation is not one of emergence, but of balance. The cosmos needed its dark architecture before it could learn to shine. It needed gravity before it could dream of radiance. It needed death before it could understand life. And that is the greatest paradox of all, that before the universe could see itself, it first had to fall into itself. In that fall, in that first silent birth of darkness, everything began. They could be older than atoms and heavier than galaxies. When we think of black holes, we imagine them as the remains of something, the corpses of massive stars collapsing under their own gravity. But primordial black holes break that rule. They are not born from death, because they were never alive. They emerged from pure imbalance, from the chaotic breath of the universe itself, in a time before stars, before matter as we know it, before even the concept of time had settled into meaning. In the first fraction of a second after the Big Bang, everything we now call existence was compressed into an incomprehensible density. Space, time, energy, all tangled in a single turbulent fabric. Quantum fluctuations, the tiny random ripples that define the uncertainty of reality, were everywhere, rising and falling like waves on an ocean of creation. Most were small, harmless, the flickers of energy that quantum mechanics predicts in every vacuum. But some, in that unimaginable density, grew monstrous. When inflation, that brief exponential expansion of the universe, stretched those ripples, it froze them into the geometry of space-time itself. Each fluctuation became a seed, a region slightly denser or rarer than its surroundings. And in a universe that was still fluid and unformed, density meant destiny. In the most extreme cases, a region could collapse inward so violently that not even the pressure of radiation could resist it. The result? A black hole born directly from the Big Bang's fabric, a primordial black hole. Unlike their stellar cousins, these entities had no parent stars, no galaxies, no supernovae. They were self-born, the first gravitational structures in existence. Some might have been microscopic, smaller than an atom, with masses less than a mountain. Others could have been gargantuan, billions of times heavier than the Sun. There was no rule to their scale, only the chaos of quantum variance deciding which patches of the early universe would survive as shadows. For decades, the idea of primordial black holes remained an elegant speculation. But then came Stephen Hawking. In 1974, Hawking proposed something that changed how we understood black holes forever. Quantum theory suggested that space around a black hole was not empty, but seething with particle-antiparticle pairs popping in and out of existence. Occasionally, one particle of the pair would fall into the black hole while the other escaped, stealing a sliver of its mass. The black hole, paradoxically, would evaporate, radiating energy, shrinking over time, and eventually vanishing. This was Hawking radiation, a quiet death for the most powerful objects in the universe. And it implied something profound, that black holes are not eternal. Small ones, especially primordial black holes, might have evaporated long ago, leaving behind bursts of radiation, faint signatures scattered through the cosmic microwave background. If such signatures exist, they are the fingerprints of the first black holes, the ghosts of the beginning. But not all would have vanished. The lifetime of a black hole depends on its mass. The larger it is, the longer it survives. A primordial black hole with the mass of a mountain would evaporate in a fraction of the universe's age. But one with the mass of a planet could persist for billions of years. Those larger relics might still wander the cosmos today, invisible, ancient, indestructible. Some physicists believe these primordial remnants could make up a significant portion of what we call dark matter, the mysterious, invisible substance that outweighs all visible matter combined and holds galaxies together. Dark matter has puzzled science for nearly a century. We can't see it, can't touch it, but we know it's there. Its gravity sculpts the motion of stars and bends the light of galaxies. If primordial black holes exist in large enough numbers, they could explain this cosmic missing mass. They would be the silent architects behind everything. An invisible population of ancient gravitational wells, shaping the universe's structure without ever shining. Imagine that every galaxy, every cluster, every filament of the cosmic web owes its existence to these hidden seeds. Tiny shadows from the dawn of time, scattered like dust across the expanding void. It would mean that before galaxies, before stars, before atoms, the universe was already building its skeleton from black holes. But how could we know? The universe, generous as it is with light, hides its deepest truths in darkness. To find primordial black holes, we must look for their gravitational effects, how they bend, distort, or amplify the light of distant stars, a phenomenon known as gravitational lensing. When a black hole passes in front of a star, its gravity acts as a lens, momentarily brightening the starlight. These events, called microlensing, have been hunted for decades, yet their signals remain elusive. Some detections have hinted at masses consistent with black holes, too small to be from stars, too large to be from anything else. Yet the evidence remains ambiguous, wrapped in cosmic noise. The universe rarely gives up its oldest secrets willingly. And so, the debate continues. Are primordial black holes the dark matter we've been searching for, or are they just another ghost story told by gravity? Even more tantalizing is the idea that these black holes might have helped form supermassive black holes, the titans that sit at the centers of galaxies. Observations of the early universe show quasars, brilliant, galaxy-sized engines powered by black holes billions of times the mass of the Sun, existing less than 1 billion years after the Big Bang. That should be impossible. Black holes formed from normal stars simply wouldn't have had time to grow that large, unless, of course, they started big. Born primordial, feeding on the newborn universe's chaos. If that's true, then primordial black holes weren't just relics. They were architects. They seeded galaxies, defined the flow of cosmic structure, and perhaps even shaped where stars could form. In that sense, they were the universe's first engineers, creating order from the formless void. Yet there is a darker possibility still. If black holes can evaporate through Hawking radiation, then the end of the universe might not be cold and empty, but loud and brief, a final flickering of countless dying primordial black holes, releasing their last whispers of energy. The ultimate fireworks of a cosmos that began and ends in radiation. Hawking once described black holes as the ultimate embodiment of entropy, the universe's relentless march toward disorder made manifest. But what if they are also the source of structure? If the same phenomena that destroy information also give rise to it, then the cosmos is a loop of paradox, a system that both erases and creates meaning simultaneously. It is here that science begins to brush against philosophy. If black holes existed before light, before atoms, before time as we measure it, then what do they represent? They are not just objects. They are the pure geometry of gravity, the shape of space-time collapsing upon itself. They are the universe looking inward, the first act of self-reflection. In quantum cosmology, the early universe may have been a sea of quantum foam, a frothing, restless field of energy fluctuations where space-time itself was uncertain. In that chaos, tiny bubbles of curvature might have formed and vanished in fractions of a second. Some of those bubbles, if dense enough, could have become miniature black holes, primordial by definition, flickering in and out like breaths. If so, then black holes and space-time were born together, inseparable. Two faces of the same reality. The black hole is not an intruder in the universe's fabric. It is the fabric, folded to its limit. Perhaps the black hole is not even an object, but a question. A place where the laws of physics turn inward and whisper, "What am I?" Theoretical models even suggest that the number of primordial black holes might determine how galaxies form, how dark matter clumps, and how the cosmic background radiation appears. If we map that background precisely enough, we might see tiny irregularities, patterns too fine to come from normal matter, too structured to be random. Those could be the shadows of the first black holes, the fossils of the beginning written into the afterglow of creation. And what if they are more than fossils? What if primordial black holes never truly died? Hawking radiation predicts their slow evaporation, but no one has ever observed it. For all we know, they could persist indefinitely, shrinking asymptotically, never quite reaching zero. If so, they are eternal, the only things that have survived every cosmic transformation since the dawn. In that case, when we gaze into the night sky, We are not just looking into space. We are looking into the graveyard of creation and its survivors. Perhaps some of those primordial black holes now drift between galaxies, silent and untouchable, older than every atom in your body. Each one a relic from the instant the universe became real, each one carrying within its darkness the memory of the first fluctuation that broke perfect symmetry. They are not stars. They are not even things. They are the universe's first scars, the evidence that perfection cannot last. And maybe that imperfection, that collapse, is what allowed everything else to exist. Without density fluctuations, there would be no galaxies, no stars, no life. Without imbalance, no creation. The universe's first act was to fracture, and from that fracture came the possibility of form. So, in a way, primordial black holes are the physical embodiment of imperfection. They are the universe's confession, its acknowledgement that to create, it must first destroy. If they are the dark matter, then every movement of a galaxy, every spiral of a star, every orbit of a planet is guided by these invisible relics. The entire cosmic ballet is choreographed by entities we can never see. In that sense, darkness is not absence. It is presence of the highest order, the structure behind all light. Perhaps this is why we find beauty in the night sky, not because of the stars, but because of the space between them, the silent architecture of everything. Science seeks to prove, but awe seeks to understand. And in that balance, we glimpse the truth of primordial black holes. They might never be seen, never confirmed, yet their fingerprints are everywhere, in the shape of galaxies, in the cosmic background, in the persistence of mystery itself. If we ever find them, we will not just be discovering a type of black hole. We will be touching the universe's own memory, the shadows it cast before it knew how to shine. They are the ghosts of the beginning, the invisible anchors that hold the cosmos together, the dark lattice upon which existence learned to take form. And perhaps, as we peer deeper into the blackness of space, it is not light we are chasing, but the memory of those shadows that came first. Light came late to a universe already haunted. For hundreds of millions of years, there had been only darkness, not the empty darkness of nothingness, but a pregnant, invisible one, heavy with waiting. Hydrogen drifted endlessly, quiet and cold. Gravity whispered, weaving invisible threads between the particles. The first black holes, ancient and silent, had already claimed their place in this abyss. Unseen monarchs reigning over a kingdom of shadows. And then, at last, something broke the stillness. Somewhere in that immense quiet, a cloud of gas collapsed. For the first time since the beginning, pressure fought gravity and won. At the center of that collapse, hydrogen atoms fused, releasing light, true light, into a cosmos that had never seen it. The first stars were born. They were not like the stars we see today. These were population 3 stars, the pioneers of illumination. Massive, unstable, almost mythic in scale. Many were hundreds of times heavier than the sun, burning with such ferocity that their lives lasted only a few million years. Their light was searing, raw, untouched by metals or dust. They blazed into existence in a universe still filled with the echoes of its birth, carving away the ancient fog of hydrogen that had hidden everything. But their birth was no coincidence. The first light didn't emerge at random. It was guided. The invisible hands of black holes and dark matter had already been shaping the cosmic landscape long before those stars were kindled. The primordial black holes, scattered like seeds through the void, had bent the flow of matter around them. Every distortion in space-time they caused became a gathering place for gas, a gravitational well where hydrogen could accumulate, cool, and collapse. Without those wells, the gas might have remained diffuse, never dense enough to ignite. So in a sense, light did not oppose darkness. It was born from it. The shadows had built the stage. Every flickering star that rose in that first dawn did so because something unseen had pulled the universe into shape. Each photon that escaped into the void carried, buried within it, the fingerprint of a black hole's gravity. The irony is almost poetic. The universe's first stars owed their birth to the very thing that would one day consume them. As the population 3 stars blazed, their radiation began to transform everything. The ultraviolet light they emitted struck the surrounding hydrogen, tearing electrons from atoms, a process called rionization. For hundreds of millions of years, this radiation slowly peeled back the cosmic fog, making the universe transparent again. It was the first sunrise of the cosmos, a dawn that stretched across billions of light years. And yet, even as the light spread, the darkness remained. Those early stars were short-lived. Their size was both their brilliance and their doom. Within a few million years, their cores collapsed, unleashing titanic explosions, supernovae, that scattered the first heavy elements into space. Carbon, oxygen, iron. The ingredients for everything that would ever live. Some stars died even more violently, collapsing directly into black holes, joining the ranks of their primordial ancestors. Creation and destruction, locked in rhythm. It was as if the universe was learning to breathe. Collapse and ignite. Collapse and ignite. Light followed shadow, and shadow followed light. One could not exist without the other. Those new black holes, born from the first stars, began to merge with the older, primordial ones. They sank to the centers of growing galaxies, accreting gas and merging again and again, their masses multiplying. Over cosmic time, these small seeds, a mix of ancient and newborn, would evolve into the supermassive black holes that anchor galaxies today. The first dawn, it turns out, wasn't alone. It came hand in hand with darkness. Wherever light was born, a black hole waited to receive it. Each star that shone contributed to the making of its own eventual grave. Astronomers studying the earliest galaxies, those seen through the James Webb Space Telescope, have found something astonishing. Massive black holes already existed less than 1 billion years after the Big Bang, far too soon for normal stellar evolution to explain. These discoveries whisper of an earlier lineage, the primordial black holes that may have acted as the gravitational cores of these galaxies, pulling gas into swirling disks that gave birth to new generations of stars. In this way, the universe's first structures were collaborations between light and darkness. The black holes sculpted the geometry. The stars filled it with glow. One defined form, the other revealed it. As the first constellations bloomed across the void, the cosmic night changed forever. The hydrogen fog thinned, and for the first time, light could travel freely across space. But this wasn't a pure triumph. With illumination came entropy. The stars burned their fuel, the galaxies grew turbulent, and energy began to flow outward. The great equalization that would eventually cool everything again. The dawn had come, but it was fleeting. Even as photons raced through the universe, their paths were bent, twisted, and swallowed by the black holes that surrounded them. These gravitational wells, the same ones that had midwifed light, now began to feast upon it. They grew, they merged, they spun faster. Imagine that moment in cosmic time, galaxies forming like ripples on a pond, their centers glowing with infant black holes devouring matter, surrounded by rings of blazing gas. The sky itself would have seemed alive, radiant rivers of light bending around invisible mouths. If one could have stood there, watching, the view would have been terrifying and sublime. Stars collapsing even as others were born. Light curving around darkness in endless choreography. The universe awakening to itself. Aware for the first time of its own beauty and violence. It's easy to think of black holes as destroyers, but in this age, they were also creators. By consuming gas, they heated and stirred their surroundings, driving winds that shaped entire galaxies. Too many stars and galaxies would burn themselves out. Too few, and they'd remain cold. The balance between light and darkness, between radiation and gravity, determined everything. Without the darkness, there might never have been light, because darkness wasn't the absence of creation. It was its foundation. The universe's first architects were the ones that consumed, not emitted. The first structures formed around emptiness. The first meaning arose from collapse. That paradox is woven into the universe's every motion. Even now, billions of years later, the stars you see at night orbit black holes that will one day inherit them. Every brilliant sunrise we know is already written in the language of decay. The early galaxies, chaotic, luminous, violent, were the direct descendants of the cosmic dark ages. The same gravitational wells that once hid in silence now hosted suns and storms of unimaginable brilliance. The black holes at their centers, once invisible, became beacons, quasars, outshining entire galaxies. Light and darkness had merged, and the result was not opposition, but unity. That unity is the universe's oldest lesson, that creation and destruction are not rivals, but reflections. The first light did not banish the shadows. It revealed them. As the Rayonization epoch continued, more stars were born, more galaxies coalesced, and space grew increasingly transparent. But the memory of that earlier silence lingered, encoded in the cosmic background, in the faint patterns of temperature and polarization that scientists still measure today. Every photon from those ancient times carries a trace of its imprisonment, the scars of a universe once ruled by shadows. And still, the black holes remained. They watched the coming of light not as victims of its triumph, but as its silent co-authors. Their gravitational fields carved the rivers through which matter flowed, defining the landscapes that stars would later illuminate. The dawn wasn't a victory of light over dark. It was a duet. Even now, that duet continues. Stars live and die, collapsing back into the darkness that first made them possible. The Milky Way itself carries a supermassive black hole at its center, a remnant of that cosmic partnership. It sleeps for now, but it remembers. In the beginning, black holes were the universe's first thought. Light was its first answer. Together, they wrote the script of existence, the pull and the radiance, the hunger and the revelation. When we look at the first stars through telescopes that peer billions of years into the past, we are not just seeing the dawn of light. We are seeing the continuation of an ancient dialogue, the same conversation between being and void, creation and collapse, that has never ceased. The first dawn was not alone. It came walking beside the shadows that had prepared the way. It came burning through a web that gravity had already spun. It came not to erase the darkness, but to crown it, to reveal that the universe's deepest truth is not light or dark, but their dance. And as that first light spread, crossing the gulfs of time and space, the black holes waited, quiet, patient, eternal. They did not chase the light. They held it, bent it, wove it into new forms. In the great cosmic tapestry, their gravity provided the threads. Light merely filled in the color. In the end, creation was not a single explosion of brightness, but a collaboration across ages. The universe learned to shine because it had first learned to collapse. It learned to speak because silence had taught it how to listen. And so, even now, every photon that touches your eye carries the memory of its origin, not just from the stars that birthed it, but from the shadows that gave it form. The dawn was never alone. It never could be, because light, in all its beauty, has always been the child of darkness. How did monsters older than galaxies form in a universe still learning to shine? Less than 700 million years after the Big Bang, when the cosmos was barely out of infancy, something impossible already existed. Black holes weighing billions of suns, titanic engines of gravity, swallowing matter faster than light could flee, were already shining as quasars, the brightest beacons in the universe. Their light, blazing from the farthest reaches of time, now reaches our telescopes like a haunting echo. We shouldn't be able to see them. They shouldn't have had enough time to grow. And yet, they did. This is one of cosmology's great paradoxes. The existence of supermassive black holes too soon, too large, too organized in a universe still turbulent and raw. The equations of physics tremble under their weight, for by all accounts, these giants are anachronisms, creatures out of order in time. To understand them, we must first grasp how long it takes to build a black hole. When a massive star collapses, it leaves behind a core, perhaps 10, 20, 100 times the mass of the Sun. If that remnant feeds on gas, dust, and nearby stars, it can grow. But even with constant feeding, accreting matter at the so-called Eddington limit, it would take billions of years to reach the scales we now observe. In the first billion years of the universe. So how did the young cosmos cheat the clock? Astronomers have proposed 3 paths, none fully satisfying, each a clue in a greater mystery. The first theory, runaway growth. Perhaps these black holes were simply born early and fed fast, outrageously fast. In the dense, chaotic galaxies of the early universe, gas was abundant and turbulence extreme. A newborn stellar black hole, only a few dozen solar masses, could have devoured matter at rates far above what theory deems stable. These bursts of super-Eddington accretion would allow it to balloon rapidly, growing millions of times heavier in only a few 100 million years. Simulations suggest it's possible, but barely. The feeding process would have to be relentless, like trying to drink an ocean through a straw without pause. The inflowing gas would heat up, generating radiation pressure that should blow the material away. Yet, if the inflow was dense enough, radiation could become trapped, dragged inward faster than it could escape, letting the black hole feast without restraint. This scenario paints the early universe as a cosmic feeding frenzy. Stars collapsing, gas streaming inward, and black holes gorging themselves to monstrous size. But even so, the numbers stretch credibility. How could something 10 times the Sun's mass grow to 10 billion in only 700 million years? That's a billion-fold increase, an astronomical gluttony that defies time itself. So perhaps they didn't start small. The second theory, direct collapse. In this view, some black holes were never tiny. They were born massive, collapsing directly from enormous gas clouds before any stars existed. Imagine a young galaxy filled with pristine hydrogen, so vast and hot that it could not fragment into stars. Instead, it collapsed as a whole, skipping the intermediate steps of stellar birth and death, folding directly into a black hole weighing hundreds of thousands of suns. These direct collapse black holes would provide a head start, a foundation for rapid growth. Fed by surrounding gas, they could reach supermassive scales in a cosmic blink. The conditions required, however, were delicate. A balance of temperature, density, and radiation that could only exist in a few special regions. Perhaps the ultraviolet light from nearby forming stars suppressed cooling, preventing the gas from fragmenting. An invisible partnership between light and darkness. If this happened even once, it could explain the earliest quasars. Yet, the evidence remains circumstantial, glimpsed only through simulations and hints in the spectra of distant galaxies. Still, the idea carries a poetic symmetry. The universe's brightest beacons might have been born from the purest collapse, untouched by any prior generation of light. But there's a third possibility, one that suggests violence, not patience, the merger hypothesis. In the young cosmos, galaxies were small, chaotic, and frequent in their collisions. Every merger was a gravitational storm, flinging stars and gas into turbulent spirals. If many small black holes populated those galaxies, the remnants of the first stars, their collisions could have created larger ones. A cascade of mergers, each more violent than the last, might have built up supermassive black holes rapidly. It's a beautiful idea, but again, the math resists. The mergers would need to occur in dense clusters with near-perfect timing. The resulting black holes would recoil from the gravitational kicks of each collision, possibly ejecting them from their hosts entirely. The odds seem cruel, and yet nature has a habit of defying our intuitions. So perhaps the truth lies in combination, a symphony of processes. Some black holes may have formed directly from gas collapse, others from stellar deaths and runaway feeding, still others from merging together in cosmic chaos. Together, They filled the early universe with seeds that grew, collided, and ignited into the quasars we now see. When we look at those quasars through the James Webb Space Telescope, when verdikwan antrella sana sanduri, we are not just witnessing light from the ancient past. We are seeing the signatures of black holes so luminous that they outshine entire galaxies. Their energy comes not from fusion, but from gravity itself, from the desperate spiral of matter falling toward oblivion. Each quasar is a paradox incarnate, a black hole, the ultimate darkness, producing the universe's brightest light. The light we see from those ancient quasars began its journey over 13 billion years ago. In that time, it has stretched, red-shifted, thinned, and weakened, carrying with it the whisper of the impossible. Some of these quasars are powered by black holes exceeding 10 billion solar masses, existing when the universe was less than 5% of its current age. The numbers should not add up, and yet the photons keep arriving. It's as if the universe is taunting us, revealing glimpses of things it shouldn't have been able to make. Every time a telescope captures a new quasar at a higher redshift, cosmologists are forced to rethink their assumptions about time, structure, and growth. Perhaps our understanding of black hole physics is incomplete. Perhaps gravity, under extreme conditions, behaves in ways we do not yet comprehend. Some researchers have even begun to wonder if primordial black holes, those relics from before the first stars, might have been the seeds of these giants. If a few of them survived, already weighing thousands or millions of solar masses, they would have needed no rush, no feeding frenzy. They would have begun the race halfway to the finish line. In that sense, the mystery of early supermassive black holes might be a continuation of the universe's original paradox, that darkness came first, and light followed its outline. If that's true, then quasars are not anomalies. They are inheritances, the flickering ghosts of black holes older than galaxies, still shaping the visible universe from beneath its glow. The evidence continues to mount. JWST has revealed galaxies far earlier and brighter than expected. Some too massive to fit current models. Their centers glow with radiation that hints at active black holes already feeding. We are peering into a time when the first galaxies were supposed to be fragile wisps, and instead we find titans staring back. These observations don't just challenge our understanding of black hole formation, they challenge our understanding of time itself. The universe was supposed to unfold gradually, matter cooling, gathering, igniting. But these quasars suggest acceleration, a cosmic impatience, as though gravity refused to wait. And in that refusal lies something profound. For all our equations and simulations, we are still haunted by a simple, human question. How could something so vast, so ancient, have arisen so soon? What does it mean that the universe's greatest abysses were also its first creators? Maybe the laws of physics are not the full story. Maybe the early universe was a different kind of place, one where density and time blurred, where gravity could fold itself more easily into infinity. Or maybe these black holes are evidence that reality itself is more flexible than we dare to imagine. The numbers remain brutal. A 10 billion solar mass black hole forming in less than 700 million years requires growth rates that exceed anything we've seen since. It would mean that the early cosmos, still glowing from recombination, was already feeding its darkest children with everything it had. Perhaps that's what the universe does best. Build paradoxes out of necessity, light and darkness, expansion and collapse, birth and death, all woven into a single act of becoming. The supermassive black holes of the early universe remind us that creation is not linear. It doesn't move step by step, but leaps, sudden, impossible acts of formation that defy causality. Somewhere between chaos and order, gravity found shortcuts. Each theory, runaway growth, direct collapse, merger, or primordial inheritance, is a fragment of the same truth, that the universe wastes nothing. Every collapse feeds a new beginning. Every impossibility conceals an inevitability. As scientists trace these ancient beacons, they confront not just the limits of observation, but the limits of comprehension. For in every quasar's glow lies the story of a cosmos that refused to wait for equilibrium, that raced ahead, outpacing its own rules. And yet, the paradox remains beautiful. The youngest parts of the universe contain its oldest hearts. The brightest light is born from the deepest void. When we gaze into those quasars, those cosmic lighthouses blazing from across 13 billion years, we are looking into the eyes of giants that should not exist, but do. Their light crosses the entire age of everything, whispering of a time when the universe, still unsteady in its infancy, had already learned to create monsters. Perhaps that is the universe's truest lesson. That impossibility is only another form of becoming. The existence of these giants is not a violation of physics. It is an invitation to expand it, a reminder that creation is not bound by patience, that even in a cosmos barely awake, gravity was already dreaming of infinity. The young universe did not fear its darkness. It grew from it. And in the glow of the first quasars, we see that dream still burning, the light of impossibility, born from the hunger of creation itself. Darkness built the universe of light. Every galaxy, every star, every world that would one day harbor thought, may have been born around a shadow. In the earliest ages, when the universe was still unrecognizable to anything like us, gravity was already at work assembling the architecture of everything to come. Invisible halos of dark matter stretched like a hidden skeleton across expanding space, forming the scaffolding upon which the first galaxies would hang. But at the heart of those halos, something even more enigmatic may have been waiting. Black holes, the silent engines of the cosmos, pulling the threads tight, shaping the pattern of the cosmic web itself. Astronomers have long suspected that black holes, especially the supermassive ones, are not passengers in cosmic evolution. They are its architects. They do not simply sit at the centers of galaxies. They define them. The evidence is subtle, but everywhere. The M-sigma relation, linking the mass of a galaxy's central black hole to the velocity of its stars, suggests that galaxies and their black holes grow together, as if one cannot exist without the other. But how could that be? If black holes are supposed to be the products of galaxies, not their progenitors? What if that assumption is backward? What if, from the very beginning, the dark came first, and the light merely followed its design? In the simulations of modern cosmology, the early universe begins as a web of filaments, threads of dark matter stretching across unimaginable distances, converging into nodes where gravity is strongest. These intersections are where galaxies form, condensing from gas that flows along the filaments like rivers into valleys. Yet within those nodes, even before stars lit the way, black holes could have formed from the densest clumps of matter, primordial or direct collapse seeds. Their gravity would have deepened the wells at those intersections, accelerating the fall of gas, amplifying the birth of galaxies. If so, then the first black holes weren't just byproducts of cosmic structure. They were the very scaffolding that held it together. Imagine it. Invisible anchors around which the first galaxies condensed, like dew forming around unseen threads at dawn. The entire luminous universe taking shape in the gravitational memory of collapse. These ancient black holes might have acted as gravitational catalysts, turning potential energy into structure, chaos into order. They shaped not only where galaxies formed, but how they evolved. Their influence extended beyond their immediate surroundings. By heating and stirring intergalactic gas, they could regulate star formation, preventing young galaxies from collapsing too quickly or burning out too soon. Paradoxically, destruction was creation's greatest tool. In those formative eons, as the first stars exploded and the universe grew transparent, black holes may have been the agents of ionization, the epoch when ultraviolet light from the first stars and quasars stripped electrons from hydrogen atoms, transforming the foggy cosmos into a clear one. But starlight alone may not have been enough. The radiation from accreting black holes, particularly in early quasars, could have provided a substantial contribution, punching holes in the cosmic veil, allowing the first real transparency of the universe. The very darkness that once cloaked everything was, ironically, what cleared the way for light to roam freely. This idea rewrites creation not as a linear ascent, darkness yielding to light, but as a conversation between them. Black holes, through their hunger, gave galaxies a center. Their gravitational fields sculpted the flow of matter, deciding where light would one day gather. Without those gravitational seeds, the universe might have remained a featureless mist, an endless expanse of uniform hydrogen. But gravity, relentless, imperfect, hungry, refused to let uniformity win. It gathered, it collapsed, it built. The cosmic web, the vast interconnected network of filaments that defines the large-scale structure of the universe, owes its form to that ancient process. In every direction we look, galaxies trace the outlines of something invisible. A dark geometry drawn by forces we cannot see but can infer. This structure is not random. It is rhythmic, fractal, repeating. The echo of quantum fluctuations stretched across eternity. And at the heart of this web, in the densest regions, lie the black holes, the unseen architects whose gravity binds the pattern together. Their fingerprints appear in the most delicate places. The clustering of galaxies, the temperature of intergalactic gas, the distribution of dark matter halos. Cosmologists now simulate entire universes, populating them with black holes to see how galaxies grow differently. And again, the simulations agree. Without early black holes, galaxies form too slowly, too sparsely. With them, structure emerges faster, richer, more complete. It is as if the universe knew, instinctively, that it needed its own shadows to find its shape. Even now, billions of years later, the same balance endures. Every galaxy, from the smallest dwarf to the grand spirals like our Milky Way, harbors a black hole at its center. These titans dictate the pace of star formation, the shape of galactic arms, the life cycle of the cosmic ecosystem. They are not passive remnants. They are the beating hearts of galaxies, dark hearts that set the rhythm of the visible world. Yet their nature remains paradoxical. They destroy information, yet their existence gives structure to everything. They consume light, yet their gravity determines where light will travel. They are chaos made into order, absence turned into architecture. From a human perspective, this inversion is unsettling. We are taught to see darkness as void, as the end of things. But the cosmos tells a different story. In the universe, darkness is generative. It builds, it anchors, it gives meaning to light. Perhaps this is gravity's great secret, that its most destructive act is also its most creative. When space-time folds inward to create a black hole, it isn't erasing existence, it's sculpting it, deepening the geometry of reality itself. The more it collapses, the more it defines. In this sense, the universe was built not by explosion alone, but by implosion, by the inward pull that gives form to outward expansion. Every star, every orbit, every cluster is a note in this harmony between collapse and flight. Black holes are the instruments of this hidden music. Their gravity weaves the melody that light follows. Their presence imposes the rhythm by which galaxies dance. When we map the cosmic web, what we are really seeing is the shape of gravity's dream, the unseen network of curvature that defines what existence can be. The awe of this realization is hard to escape, that every beautiful spiral galaxy, every shimmering nebula, every cradle of light was once drawn inward by something utterly invisible. The universe's masterpieces were sketched in the ink of its own oblivion, and the more we study them, the clearer the pattern becomes. Supermassive black holes and their host galaxies evolve in tandem, one feeding the other, one restraining the other, like partners in an endless cosmic dance. When the black hole feeds, it releases torrents of energy, blasting out winds that shape the galaxy's gas, triggering or halting star formation. When the galaxy grows, it supplies the black hole with new fuel. Together, they write the history of cosmic evolution. This unity between creation and destruction echoes something deeply philosophical, perhaps even spiritual. If the laws of physics could speak, they might whisper that wholeness arises from opposition, that the universe's harmony depends on its own extremes. The cosmic web, with its delicate filaments of galaxies, is not a random accident. It's the residue of a universe learning to balance itself between the outward push of expansion and the inward pull of gravity. And in that balance, black holes are the mediators, the sculptors, the quiet architects who turned chaos into design. There's something humbling in that thought, that everything bright and alive in the cosmos, every photon that ever touched our eyes, every atom that ever formed a living cell, was born from a universe ruled first by gravity's darkness. We tend to think of ourselves as creatures of light, but in truth, we are the children of collapse. The iron in our blood, the calcium in our bones, the carbon in our cells, all were forged in the deaths of stars, which themselves were born in galaxies defined by black holes. We are, quite literally, the descendants of destruction. Perhaps that is why the night sky speaks to something ancient within us, why the darkness above doesn't feel like emptiness, but like belonging. It is a mirror of our origins, a reflection of the shadows that made us. Every galaxy is a monument to that truth, a cathedral of light built upon invisible foundations, and though we cannot see them, those foundations endure. Black holes, holding space together with a patience beyond measure. We owe our existence to their silence. And as we map the universe, tracing filaments of light, cataloging clusters, measuring redshifts, we are, in a sense, sketching the outline of the unseen. Every glowing structure is a lantern hung upon a thread of gravity's memory. The black holes remain hidden, but their design is everywhere. In the grand equation of existence, darkness is not the counterpoint to light. It is its cause. The same gravitational hunger that devours also creates, folding potential into pattern. So when we look into the sky, what we see is not a war between radiance and void, but a collaboration, the echo of gravity's creative fall. The universe, it seems, was never afraid of its own darkness. It used it to build everything, and perhaps that is its most profound revelation, that to create beauty, reality first had to break itself, that to make galaxies, it first had to collapse, that the cosmos itself, and everything conscious within it, was shaped by the quiet, invisible architects who worked in shadow, so that light could one day be born. Light feeds the darkness that birthed it. It is the oldest rhythm in existence, the cycle of creation folding back upon itself. Once darkness gave rise to light. Now light returns the favor. The universe, vast and ancient, continues its endless exchange, where radiance and shadow are not enemies, but dance partners in the same infinite waltz. Every photon we see today has, in some way, passed through a shadow's domain. The starlight that fills our sky, the glow of distant galaxies, even the cosmic background itself, all have brushed against gravity's invisible hand. For while stars shine, black holes wait, and sooner or later, the light finds its way back to them. At the heart of nearly every galaxy, including our own, lies a supermassive black hole, the final heir to an ancient lineage that began before the first dawn. For billions of years, these cosmic giants have shaped the galaxies around them, feeding on the light that once depended on them to exist. The cycle is perfect in its symmetry. The shadows that built the universe now consume it, one photon at a time. But black holes do not merely devour, they transform. When matter falls toward them, it doesn't vanish instantly. It spirals inward, forming an accretion disk, a whirling storm of gas and dust, heated by friction and gravity to temperatures so extreme that it shines brighter than any star. Paradoxically, the darkest places in the universe produce its most radiant light. This is the secret of quasars, those brilliant beacons we see across billions of light years. They are powered not by fusion, but by annihilation. Matter falling into black holes, releasing energy in its final moments. Each flicker of their light is a record of destruction and creation fused into one. Around the accretion disk, magnetic fields twist and knot, launching jets of charged particles that blast out at nearly the speed of light. These jets pierce the galaxy, spreading energy across thousands of light years, stirring clouds of gas, triggering bursts of star formation, or snuffing them out. This process, known as AGN feedback, is the cosmos regulating itself. Black holes don't simply end things. They control the tempo of creation, ensuring the universe never burns too fast or fades too soon. It's a cosmic paradox. The most powerful destroyers also act as caretakers. They give galaxies their rhythm, their heartbeat. Too much light, and chaos reigns. Too little, and darkness wins. The balance lies in their union. In this way, the universe is not a battle between opposites, but a feedback loop. An elegant self-portrait painted in gravity and glow. The light of stars gives rise to matter that will one day feed black holes. The energy released from those black holes seeds the birth of new stars. The cycle repeats, endlessly refining itself. The cosmos doesn't choose between creation and annihilation. It uses both. When we look at the spiral arms of galaxies, we are seeing this balance made visible. The sweeping arcs of stars and dust are shaped by gravity's pull and light's outward pressure. Each galaxy is a living yin-yang, a rotating harmony of opposites. Brightness wrapped around darkness, order spinning within void. In every cosmic storm, light falls into darkness, and darkness gives light its shape. It is this equilibrium that keeps the universe alive. Without collapse, there would be no structure. Without radiance, no renewal. Gravity and energy, pulling and pushing, forever holding each other in tension. And at the center of it all, the black holes, not silent, but singing, if one knows how to listen. Their accretion disks hum in X-rays and ultraviolet. Their jets roar across the radio sky. We can't hear them directly, but their influence resonates through the cosmos like the deep notes of a hidden symphony. It's easy to imagine these titans as devourers, endlessly consuming. But in truth, their hunger creates balance. The energy they release through accretion and jets keeps galaxies from collapsing under their own brightness. Too much gas, and stars would form uncontrollably, burning their fuel too quickly. Too little, and galaxies would fade into darkness. Black holes sit at the center, ensuring neither extreme wins. They are not the end. They are the regulator, the boundary between chaos and order. Every photon that falls toward them, every particle that spirals inward, contributes to this vast, delicate equilibrium. Even as light vanishes, it is not wasted. The gravitational energy released during infall is converted into radiation, sending waves of brilliance across space before the final plunge. Nothing is lost. It is only transformed. Perhaps this is why the universe seems both tragic and beautiful, because it survives through its own contradictions. It creates by destroying. It brightens by consuming. It expands by collapsing. The more we study the physics, the more poetic it becomes. When light falls into darkness, it releases more light. When energy yields to gravity, it fuels rebirth. The mathematics of accretion, the heat, the turbulence, the radiation are the physical translation of an existential truth. Everything ends, and in that ending, something new begins. Even our sun will one day contribute to this grand cycle. It will exhaust its fuel, cast off its outer layers, and leave behind a white dwarf, faint, fading. Over eons, its remnants will drift through space, perhaps drawn into the gravitational field of a black hole, completing the journey that began when the first light was born. Every photon it ever emitted, every warmth that ever touched life, will someday belong to the darkness that once shaped it. And yet, there is no despair in this. The act of falling, of light returning to shadow, is not a loss, but a reconciliation. The universe doesn't waste its radiance. It recycles it, endlessly folding it back into itself, ensuring that every spark, every atom, every beam continues the eternal exchange. When a black hole feeds, the surrounding space glows with extraordinary brilliance. It's as if the universe refuses to let destruction happen quietly. Even collapse is luminous. Even oblivion shines. Astronomers studying active galaxies have found that this cycle of feeding and feedback determines the very lifespan of galaxies. When the central black hole becomes too active, it blows away the surrounding gas, halting star formation, a period of cosmic quiet. When it rests, the gas cools and falls inward again, reigniting creation. Light and darkness take turns, each granting the other its moment. This alternation is not random. It is rhythmic, almost biological. The universe breathes through it. Expansion and collapse, radiation and absorption, existence and return. If the cosmos has a heartbeat, it is this, the steady pulse of matter falling inward and energy streaming outward, an infinite rhythm of giving and taking. And so, the story that began with light emerging from darkness circles back to its beginning. We are once again in the realm of shadows, but now we understand them differently. They are not the absence of light, but its homecoming. Light falls into darkness not to disappear, but to complete itself, to remind the cosmos that nothing truly ends. It merely transforms. It is tempting to see the black hole as a devourer of hope, a final erasure, but perhaps it is closer to a memory, a record of what once was, compressed into eternity. Every photon it consumes adds to its mass, deepening the gravity well that shaped the universe in the first place. The black hole doesn't end the story, it keeps it. And if we could somehow stand outside time, watching the rise and fall of galaxies, the ignition and extinction of suns, we might see the universe for what it is. Not a struggle between light and dark, but a single, continuous breath. Light rises, light falls. Gravity listens. Perhaps that is the secret symmetry of existence. That everything luminous longs to return to silence. That every act of shining carries, hidden within it, the memory of collapse. The cosmic cycle is not cruel. It is complete. The photons that once lit the early universe now fall into black holes that were born before them. The same shadows that built the first galaxies now cradle their remains. Creation and annihilation are not separate. They are one heartbeat, the inhale and exhale of reality itself. So when we look up at the night sky, when we see the faint light of distant galaxies crossing billions of years to reach us, we are witnessing a miracle of endurance. Light that has escaped countless shadows, yet still belongs to them. Every ray of light is a traveler, destined eventually to fall back into the darkness that gave it life. And that is not tragedy. That is balance. The universe began in darkness, and it will end there, not in despair, but in harmony. Because even when light falls into darkness, the darkness remembers, and through that memory, existence continues. Perhaps light wasn't the beginning, it was the awakening. Long before the first stars shimmered, before any color graced the void, the universe already possessed memory. It existed not in light, but in gravity, written into the folds of space-time by the first black holes. They were not creations of brilliance, but of collapse, not explosions, but impressions. Marks pressed into the universe's fabric by the weight of its own becoming. Those ancient shadows were more than objects. They were the first records, the first proof that the universe could remember itself. Every particle that fell, every wave of energy that curved around them, left an imprint on the geometry of everything that followed. Long before light could reveal the cosmos, darkness had already written its script. When we speak of memory, we usually mean neurons, minds, recollection, the human gift of time. But memory began long before we did. It began when gravity first learned how to bend space, when energy learned to curve into form. The black holes that preceded the dawn were the universe's first act of remembrance, preserving within their silence the history of every collapse, every spark, every motion. And perhaps that is why, billions of years later, consciousness emerged. Because the cosmos, through us, wanted to remember again. In our curiosity, in our questions, in our quiet awe before the night sky, the universe rediscovers what it has always known: that light and darkness are not rivals, but reflections of the same truth. The act of awareness is itself gravitational, attention bending the vastness of experience into meaning. We are the continuation of that same pattern. The universe learned to look inward through us, the descendants of starlight shaped by shadows. The same gravity that once folded hydrogen into black holes now folds thought into reflection. The same darkness that sculpted galaxies now shapes wonder within the human mind. Maybe that's what consciousness truly is. Not an accident of biology, but the cosmos remembering itself through fragile forms of light. Each moment of awareness is a small echo of the first gravitational collapse, when the universe learned to turn inward, to fold upon itself, to see itself from within, and in that light, the story of the cosmos becomes a story of recognition. The black holes were never just cosmic abysses. They were mirrors waiting for eyes to look back. Every photon that falls into their darkness is an exchange, a message sent and received, a reminder that creation and annihilation are simply two directions of the same gaze. We often think of light as the symbol of knowledge, of understanding, of revelation. But what if meaning was born in the dark? What if the universe's first thought wasn't illumination, but depth? Light shows what exists. Darkness shapes why it exists. Without the shadows, there would be no contrast, no structure, no way to measure the passage of light. Every galaxy gleams only because it swims in darkness. Every idea shines only because of silence behind it. The black holes that began everything were not flaws in creation. They were its first focus, the universe learning to hold itself together. And perhaps they never waited for light at all. Perhaps, as the first photons burst forth, they did not resist them. They became them. The gravity that once devoured now reflected, transformed, and guided. The same curvature that shaped the first collapse now shaped the first rays. The darkness became radiant by remembering what it had always been, potential waiting to awaken. We, too, carry that paradox. Within every atom of our bodies lies a history older than light, forged in the hearts of stars that died, in galaxies sculpted by ancient shadows. The iron in our blood once orbited black holes. The carbon that makes our thoughts once drifted through darkness older than time. When we look up at the night sky, we are not separate from what we see. The universe is not out there. It is in us, remembering itself in the brief flicker of our awareness. The light that reaches our eyes is ancient, but the mind that receives it is older still, born from gravity, from the hunger of existence to feel its own weight.